Uh, Welcome to all of you in this course uh, on algebraic topology. So basically, this is an introductory course uh, in algebraic topology. So first of all, what is the goal of this course? So let us see. Uh, uh, so first we will start with the uh, fundamental group, right? So uh, fundamental group of a topological space, a topological space, fundamental group of a topological space. Then some techniques to compute fundamental group. Then uh, uh, homology, then some applications of homology. Homology of a topological, so this is homology group of a topological uh, space, and some applications of homology. Uh, Next, I will give references. Algebraic topology by E.H. Spanier. Second, uh, is uh, algebraic topology by Ellen Hatcher. Algebraic topology by Ellen Hatcher. Third is algebraic topology, and introduction by William S. Macy. Then fourth, uh, an and introduction to algebraic topology by J.J. root 9. Uh, so first of all, what is algebraic topology, right? Uh, so before we start uh, discussing what is algebraic topology, first uh, we should know what is actually topology. So what is topology? What is topology? So topology is study of topological spaces and continuous maps, continuous functions, right, between topological spaces. So it is expected that before you start learning this course on algebraic topology, it is expected that uh, you have an elementary knowledge of uh, uh, the courses like general topology. So general topology, algebra, and set theory. So these things, it is expected that you have already learned these things before you start uh, taking this course on algebraic topology. Next, uh, so I was discussing what is a topology. Now, so this is similarly what is group theory. So basically, we can say that group theory is uh, study of groups and homomorphisms between groups. A similar kind of definition can be given for other uh, courses actually. So what we do actually in algebraic topology. Uh, so so in topology, there is a problem of characterization, right? So given any two topological spaces X and Y, given any two topological spaces X and Y to topological spaces. Now, how to know that whether they are uh, uh, is equivalent to each other. So there is in given any field of study, whether it is topology or group theory or other field. So given any two objects, right, uh, of study, there is a concept of equivalence, right? So in topology, in general topology, given any two topological spaces, that equivalence is called homeomorphism. So in group theory, given any in group theory, equivalence between two groups is actually uh, uh, isomorphism. It is called isomorphism. Similarly, uh, if you take set theory, then equivalence between two sets is actually the uh, bijective function, right? So two sets are called equivalent if there is a bijective function between them. Now, so so we were talking about characterization problem. So given any two topological spaces X and Y, how to decide whether uh, X and Y are homeomorphic or not, right? So uh, in general, this may be extremely difficult. It may be extremely difficult to decide in general. In some particular cases, there may be uh, easier ways to decide, but in general, it is extremely difficult. So in algebraic topology, what we do is following. So given uh, any topological space, we associate it to an algebraic uh, object, right? Like group, ring, anything, right? Given any topological space X, BS to this we associate a uh, an algebraic object fx, right? So there are so many different ways of associating this an algebraic object to a given topological object, in fact, a topological space. Uh, Also, given any continuous function f from x to y, where x and y are two topological spaces, we associate it to it a homomorphism, right, from fx to fy. So suppose if we associate x to a group fx, uh, suppose if we associate a group fx to x, then to this continuous function f, we associate a group homomorphism f from here to here. Now, what is the use of this? Uh, so, what is use of this kind of association? Uh, So, so this association is in such a way that if x and y are this association is in such a way that if x and y are equivalent, then fx and fy will be equivalent, right? So uh, mostly this association actually reflects uh, some only a particular aspect of this topological space, right? So converse is not true. So if x and y are equivalent, then fx and fy will be equivalent, but converse uh, may not be true. That is, if fx and fy are equivalent, then x and y may not be equivalent. Yeah. So what we do is, if uh, fx and fy, so we said that if x and y are equivalent, then fx and fy will be equivalent. Now, if we can, because there are so many given any two groups, there are so many techniques available to decide whether they are equivalent or not. So if we can decide that fx and fy are not equivalent, then definitely x and y will not be equivalent. So this is the idea. So using to decide to solve topological problems, you uh, convert it into an algebraic problem, you solve it, right? And then you conclude the solution of algebraic problem. So, I mean, it solves many of the problems uh, in topology. Uh, Now, this kind of thing is there, you see, in geometry, right? In analytical geometry, what you do is that given uh, any geometrical object, you associate it to certain equation, right? So given in analytical geometry, given any geometrical object like line, plane, sphere, or other geometrical object, you associate it to an equation, right? And then you using those equations, you do your calculation and you decide. You solve the problems in geometry by using those equations. So, but there is one difference that there, uh, given any so that in this process for analytical geometry is actually reversible. Uh, but in this case, for in algebraic topology, this association, this is not reversible. What does it mean? Given any two geometrical objects, x and y, if x and y are different, right? If x and y are different, then you can find different then equations representing x and y will be different. But uh, in this case, it is possible to have x and y which are different, but fx and fy are same, right? So There is one-to-one correspondence in this case in analytical geometry between equations and geometrical objects. There is one-to-one correspondence, but in this case, this is not the uh, in the case of algebraic topology, this is not true. So this is a fundamental technique uh, given any problem in any field, converting it to some another problem, right, in some other field, and then solving that and then concluding the solution in the uh, previous field. So we will be discussing these things in detail. So I said that there are many ways of associating x to fx. So one way is this homotopy group or fundamental group, right? So fundamental group is a kind of homotopy group, right? So one way is the fundamental group. Another is homology group, right? So given any topological space, you associate homology group. Uh, Categories and functors. So definition of category. So a category C consists of first uh, a class of objects, the for every ordered pair x y of objects a set home xy a set home xy of morphisms with domain x and range in y. If f is in home x y, then we write f is from x to y, like this. Next, for every ordered triple x y and Z a function associating the function for every ordered triple x, y, z of objects in C are a function associating to a pair of morphisms associating to a pair of morphisms f from x to y and g from y to z. uh, they are composite. They are composite f t from x to z, satisfying following properties. First is associativity. Associativity. So if f is from x to y, g is from y to z, and h is from z to w, then we have f compose g compose h equal to h g f, which is from x to w. Next property is this existence of identity. For every object y, there exists a morphism I y I y from y to y, such that if f is from x to y and if f is from x to y, then this f compose I y equal to f and I x composed f equal to f. This IY is called identity morphism of Y. Given morphisms F from X to Y and G from Y to X, such that F is called uh, right inverse of G, and G is called left inverse of